Hi everyone. Today we're going to study exponential distribution. Exponential distribution describes the time between events in a Poisson process. That means a process in which events occur continuously and independently at a constant average rate. Examples of random exponential variables are the time until a radioactive particle decays. Another example, the time it takes before your next call. Exponential distribution is widely used in reliability studies as a model for time until failure for a device. There are associated functions of exponential distribution. For an item or system whose lifetime follows on exponential distribution, first function, we have this probability density function. It is denoted by small f of t, and this is equal to lambda times e raised to the product of negative lambda times t. Lambda here is the failure rate of the item. Second function, cumulative distribution function. This is denoted by capital F of t equals 1 minus e raised to the product negative lambda times t. Number 3 is the survival or reliability function, denoted by capital R of t equals e raised to negative lambda times t. Number 4 is the hazard function, denoted by small h of t, and this is equal to lambda. Number 5 is the mean time between failures, or expected value, denoted by capital E of x. For this, we use this MTBF as notation, equals 1 over lambda. Number 6, cumulative hazard function. This is capital H of t equals lambda times t. Number 7 is the variance, denoted by var of x equals 1 over lambda square. Let us see example 1. Assuming constant failure rate, a system has a failure rate of 2 times 10 raised to negative 3 failures per hour. What is the mean time between failures? The lambda here equals 2 times 10 raised to negative 3. We can express this as decimal as 0.002. Our formula for the mean time between failures, or MTBF, equals 1 over lambda. We simply substitute the value of lambda. It becomes 1 over 0.002. When we simplify this, we will get 500, and this is in hours. This is the final answer. Example 2. Assuming constant failure rate, a component has a failure rate of 5 failures per 10 raised to 6 hours. What is the probability that the component will still be working after 10,000 hours of operation? Our lambda here is written as 5 failures per 10 raised to 6 hours. Or simply we can write 5 times 10 raised to negative 6. We can express this as decimal into like this. And the T is given as 10,000 hours. This problem is about survival or reliability function. And we have this formula. Capital R of T equals E raised to the negative of lambda times T. We substitute the corresponding values. This becomes R of 10,000 equals E raised to the negative of 0.000005 times the T is 10,000. We can simplify the exponent product into negative 0.05. Using our calculator, we can simplify this value into 0.951. This is the final answer. Example 3. Assume that a guided missile has a true mean time between failures of 2 hours and constant failure rate. What is the probability of the missile failing to complete a 2-hour mission? Given is the MTBF equals 2 hours. We know that this MTBF equals 1 over lambda. In this equation, we can solve for the lambda. We change the position of these 2 and the lambda, so lambda is equal to 1/2 or 0.5. Another given in the problem is the time, and this is 2 hours. In this problem, the question is the probability that x would be less than 2. And this is equal to the capital F of 2, which means this is about cumulative distribution function. Our formula is capital F of t equals 1 minus e raised to the negative lambda times t. When we substitute the values, it becomes f of 2 is equal to 1 minus e raised to the negative of the product 0.5 times 2. The exponent of e is simplified into negative 1. We simplify this e raised to negative 1 as 0.368. Then we get the difference. So it becomes 0.632. This is the final answer. I hope you learned something from this video. See you again next time.